My gosh, it's the most frustrating thing in the world. Look at this. I'm pressing the exact same spot and it won't turn. Stupid. I hate this change. Can never get used to it. Okay, welcome back to quantum field theory. Um, Intro to quantum field theory. We're on episode 19 and talking about the Dirac equation, specifically the interpretation of what it tells us is happening. And basically what spinners are then. So what's happening, what these Dirac spinners are doing. So solutions to the Dirac equation behave like scalar fields, i.e. they are wave-like, but they have internal structure, whereas scalar fields do not. So what do I mean by this? I mean that in general, you have a Dirac spinner, which is dependent upon spacetime position, and there's going to be a component C and some component F, which is fully reliant on its position. And this right here will be the internal structure, and this is going to be the space-time structure. So the space-time structure, which is C, or sorry, not Phi, F, this is going to be just like what we had in the Klein-Gordon equation. So everything from that video stands. It's just the dot product between a vector or the wave vector and position, which is e to the negative I omega t minus k dot x. Yep, so that's what we have for the space-time structure component of a Dirac spinner. So what we're really interested in then is this, which is the internal structure. So recall that a Dirac spinner, a Dirac spinner is really two vial spinners, meaning that the Dirac spinner is going to just be a column where you have the vial spinner. You have a left-handed vial spinner and a right-handed vial spinner. So for alpha, which has 1 and alpha 2 components, this is a left-handed vial spinner. And then there is the right-handed vial spinner. So this is what the internal structure is going to basically talk about, or basically convey, is that they are different components of a vial spinner. And then the components will actually vary with, you can pull out the space-time structure. I like coefficients. So you can get that for a, what do you call it? Left-handed particle that is spin up, and for a right-handed particle that is spin up, you also have a left-handed particle that is spin down and a right-handed particle that is spin down, or particle field, blah, 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 which these are. Let's just put these across. And this is the Dirac spinner. So 1, 0, 0, 0. Then for spin down, 0, 1, 0, 0. 0, 0, 1, 0. And 0, 0, 0, 1. These are the components that the Dirac spinner has. So alpha, beta, it really has these 4 components. The top one talks about left-handed spin up fields. The second one, the left-handed spin down fields, then right-handed spin up, right-handed spin down. In general, in general, a Dirac spinner is a superposition of these components. We will eventually derive the solutions to the Dirac equation, but for now, let's just take a look at the solutions. So solutions look like this. We have C1 or C1 e to the negative I m t. M is the mass, t is the time, and then times the structure 1 0 1 0. Then you can have another one, C2, which is the same space-time structure, but instead it's spin down. Likewise, A, there is this tilde version, which is negative 1 1 0, C2, which is IMT, then 0 negative 1 0 1. So to understand what these solutions are telling us, let us take a look at the evolution in time of a single component Dirac spinner. So let's look at the time evolution of a field that is left-handed and spin up at time equals 0. So if we have time equal to 0, then we have that c of 0, so time equals 0, is just the spin up component for left-handed particles. But we can actually see that it is 1/2 times 1 0 1 0 minus 1/2 negative 1 0 1 0, because the 1/2 here, this will add this negative sign will cancel with this negative sign, so you'll add and get 1 here, but this negative sign won't cancel here, so you'll get 1/2 minus 1/2, so you get 0. So you can see that at time equals 0, the particle that is left-handed and spin up is equal to the first solution, or 1/2 rather, 1/2 of the first solution minus 1/2 the second or the tilde solution. Of course, these are, I forgot to put that these are time equals 0. And then if we have time is equal to pi over 2m, then you can look at this now. Pi over 2m. Well, we know that it's going to be just these at, so 1/2 C1 at pi over 2m minus 1/2 C1 tilde pi over 2m. So this is going to be 1/2. I'm just going to pull out the 1/2 here. E to the negative I pi or m pi over 2m. And then 1, 1, 0, 0 minus e to the I m pi over 2m negative 1, 0, 1, 0. Okay. And then this is just e to the negative pi over 2, e to the I, negative I pi over 2. And this is e to the I pi over 2. And at pi over 2, cosine is equal to 0. So pi equal to cosine is equal to 0, which means that these are just going to return sine at pi over 2, which is just 1. So we're just going to get I. This whole thing will just be equal to I. This is negative I. So we get 1/2 I 1, 0, 1, 0, or minus I, sorry, and then minus I minus 1, 0, 1, 0, which is just going to be equal to minus I 0, 0, 1, 0, which this is just the definition of a right chiral field. So this right here is just a right chiral spin up field. And so what we've seen is that over time, a left chiral spin up field, so perhaps I should put this in just for emphasis, left chiral spin up, over time becomes a right chiral spin up particle. So what this means is that solutions to the Dirac equation oscillate in time between left chiral spin up and right chiral spin up. Now, of course, you could also have the opposite happen where you have a solution that is spin down. So you have left chiral spin down and right chiral spin down solutions. Well, um, technically, I think that these are matter antimatter solutions. I'm not exactly sure. I haven't double checked that yet, so don't quote me on that. But essentially, you oscillate between left and right chirality, which makes sense. If you have, for example, say something go this way, then this way, this way, this way, you can see how something would or could oscillate. So let's say that this one is left-handed, right-handed, left-handed, right-handed. And it turns out that these parts where you're actually, so this is left hand spin up, then this becomes right hand spin up, then it becomes left hand spin up, it becomes right hand spin up again. These actually correspond something we'll see in a much later video. These will actually correspond to Higgs interactions. So these particles, fundamentally left-handed particles and right-handed particles move at the speed of light. But then they interact with the Higgs mechanism, which spontaneously, which will switch them between being left and right-handed. And so that basically slows them down and adds like a mass term. So let's see. We can see how this effectively generates mass in a space-time diagram. So I'm gonna go here and gonna make a big arrow there, make a big arrow here. This is time. This is space, or I'll call this R. And then you, of course, have the speed of light at a 90-degree, which I will put as a dotted line like this. So you have your velocity, magnitude of your velocity is equal to the speed of light here. Massless particles will travel along this line or at a 45 degrees this way. So if we have something, um, say we start with a field that goes here, and then it goes the other diagonal. I don't know if this is completely diagonal, so let me, yeah, okay, so more or less diagonal, and then like this. It's hard to get the angles right here. There we go. So it continues like this. Well, we can see that if we actually average out the, if we average out the position of this thing, it actually acts like a, um, it actually acts like a particle with mass that's traveling less than the speed of light. So it goes at the speed of light in this direction. It switches directions um, because it's suddenly left or right chiral, so left chiral, right chiral, and goes. And you actually look at the time average position, it is like it's traveling less than the speed of light. And so that's how effect basically has mass, because anything that travels less than the speed of light has mass. So it goes from being a phenomenon that is massless to being a massive phenomenon via the Higgs mechanism. And things that oscillate quicker have more mass. So I'll give an example with this. So if it goes this way, then okay, like this, and it keeps going like this. You see that when it switches back and forth more often, it looks like a particle that has, oh, that's, looks like a particle with more mass. So we time average, or kind of average out its position. You can see that it looks like it has more mass. So things that oscillate faster look like they have more mass. And this is what the Dirac equation is telling us. It tells us that left-handed particles switch into right-handed particles, and right-handed particles switch into left-handed particles. Or rather, the field configurations switch between each other, but you get the idea. It goes between left and right. And technically, this is actually an oscillation. It'll be like this. So it's going to oscillate really around these points, not like like a zigzag like I've done here. Yeah. And you can see that I didn't do the average exactly right here. So like technically this thing, or I didn't do I'm not good at drawing basically, but you can see how the averages look different. So that's what the Dirac equation is telling you. It's going back and forth between different left and right chiral fields. And in reality, it's oscillating because of this term. And notice that uh, because if the mass is higher, then, or like if the mass is bigger, then this time right here is going to be much smaller because this mass term right here is going to make it smaller, which means that the frequency is going to be much higher. This is basically what the mass term is right there. It's like a frequency. Yep.